Hey, welcome back. Today we're going to be specifically learning about what is Newton's third law. Newton's third law. When a force is exerted on an object, that object exerts an equal and opposite force back. Examples that I typically talk about, I've always had some students says, no, I don't believe in Newton's third law. And I say, well, okay, if you don't think an object's going to push back with the equal and opposite force that you push on it, I want you to go over there and headbutt that door as hard as you can. And I think, I've never once had a student who's willing to go do that. Why? Because they know that door is going to hurt. And the only reason it would hurt is if you push some type of force against the door is going to push back. I don't know if they always believe it's equal, but they definitely believe there's an opposite force coming back at them. Same thing. If you were to punch some type of block wall, the reason your hand breaks is because the wall pushes back with an opposite force. And for right now, you're going to have to accept that we say it's equal and opposite. And we're going to talk about this here in a little bit. For every force, action, there's an equal and opposite force reaction. And what that really means is that the force acting on object 1 due to 2 is equal to the force acting on 2 due to 1, but it's going to be in the opposite direction. That's what the negative stands for. Note that the action-reaction force acts on different objects. So this image shows how a block exerts a downward force on a table. The table exerts an equal and opposite force on the block, called the normal force. So in this case, the weight is pushing down. So if there's a force pushing down on the block, and that's its weight, why is it not sinking? Because we know that if we apply a force, according to Newton's second law, which describes what happens when a force is applied to a mass, it causes that mass to accelerate. So if this block right here is not accelerating, right, then there must not be a net force acting on this block. There has to be some type of force pushing in the opposite direction. And that force we typically describe as the normal. And right here they're showing that normal force over here. So when a weight pushes down on a surface, the surface pushes back up with what's called a normal force. And we'll talk more about that in class, but basically the normal is going to be perpendicular to the surface. And down here, what they're letting you know is that the sum of the forces, and we're going to talk about the sum of forces equation today quite a bit, is equal to the normal. The normal is going in one direction minus its weight in the other direction. And that's going to be equal to the mass acceleration in the y direction, and that's equal to 0. And how do we know it's equal to 0? Because the block's not moving. It's not accelerating. I shouldn't say it's not moving. It's not accelerating, which means it's not gaining speed and it's not changing direction. Alright, this figure illustrates the action-reaction forces for a person carrying a briefcase. Is there a reaction force in B? If so, what is it? Well, let's look at example A here first. So this briefcase, if this person's standing there and this briefcase then is not accelerating, and we're going to assume that it's staying still, it's not going up, it's not going down, it's not changing direction, then we'd have force 2, right, on the briefcase would be its weight. All right, and that's going to be a downward force. The person has to be pulling up with a force that is opposite and equal to the weight. Right? So it's not the normal because we're not really on a surface, but it's kind of like the normal in the fact that it's pulling up and it's opposite in direction of the weight of the briefcase. If this person were to not be able to, let's say we had a little child who all of a sudden we handed this off to a little child who was not able to pull up on the briefcase with a force that was equal to its weight, then the briefcase would start to accelerate downwards. Likewise, if we had a Hulkamaniac or give it to the Hulk, and he started to pull up on it, the briefcase would then be accelerated in the upwards direction because he was pulling up on it. I guess it could be a She-Hulk as well. Pulling up on it with a force that is greater, so the net force would be in the upwards direction, so it would start to accelerate upwards. And we have all types of balanced forces. This person down here is standing this person's weight is acting down, and then the Earth is pushing up. And this would be a normal force because it's a surface that's pushing up. And I really need to draw that vector a little bit longer so that these two are opposite and equal. What would happen if the normal in this case were greater than the weight? Well, that means there'd be a net force of some magnitude in the upwards direction. This person would actually start to elevate. They would start to go up. And likewise, if the gravitational force was greater than the normal force, then the person would start to sink because there'd be this net force going down. So they'd start to actually accelerate, not just sink at a constant speed, but go down faster and faster and faster. All right. All right, so Newton's third law. What is Newton's third law? Go ahead and answer that. I'll catch you guys on the flip side.